Hello students, this is Mr. Allen. Today we are going to look at section 2.1, which is on basic differentiation rules and rates of change. Our objectives today is to find the derivative of a function using some basic rules, to find derivatives of the sine and cosine functions, and to use derivatives to find rates of change. Our first rule is the constant rule, and this rule basically says the following. If you have a constant c, like 2, and you do the derivative of it, the answer is 0. And that should kind of make sense, because if you think about any constant function, it's just going to be a horizontal line, like y equals 2, for example. Well, what's going to be the slope of the tangent line of that curve? Well, it's 0. Our second rule is the power rule. This is probably the most important rule for you to know. And the power rule is as follows. Say you have a function x to the n, then the derivative of x to the n is n x to the n minus 1. So for example, if I told you that y was equal to x to the third, then dx of x cubed is simply identify your exponent. So your exponent here is 3. That number goes to the front. You leave the variable the same, so it's x, and then you got to subtract 1 from the exponent, so then it's going to be 2. So this is your power rule. The exponent comes to the front, and then decrease the power by 1. When you're using the power rule, in the case of n equals 1, it's best thought as to separate differentiation rule. That is d dx of x equals 1. So for example, if we have this function y equals x, which we do right here, what's going to be the slope of that tangent line? Well, if you think about it, what's the slope? The line is not a curve, so the slope is the same everywhere you look at this curve, and that slope is going to be 1. Now, we could still use the rule y equals x to the first. When I do the derivative of that, so that'd be y prime, I could still use my power rule, put the 1 in the front, and then you have to subtract the exponent by 1. Just remember that x to the 0 is also 1, so this is still 1. Here are some more examples of using the power rule. I've already done example A. You can look at example B, which has a rational exponent. You'll get a final answer here. Note that this becomes negative. And then I did one with the x squared in the denominator. These bottom ones tend to be the ones that students get a little confused on. In example C, note that before differentiation, the 1 over x squared was rewritten as x to the negative 2. Then just use your power rule. So here was the given. You're going to then rewrite it as x to the negative 2. Then do your power rule, differentiate, and then finally simplify. Remember, in this class, I would prefer no negative exponents. The constant multiplier rule, this is kind of just a combination. I'm sorry, I'm getting ahead of myself. The constant multiplier rule is this. If you have a constant in front of a function and you're doing the derivative, you can just pull the constant out to the front. And I think it's easiest just for me to show you an example of that. So let's say I have the function y equals 2 over x. I claim that y prime, which by the way is the same thing as dy over dx based on our previous presentation, is going to be equivalent to 2 times the derivative of 1 over x. That's my claim. No, by the way, the derivative of 1 over x, we can use our power rule, so let's just go ahead and do that. The derivative of 1 over x, I'm going to rewrite that, so that'd be x to the negative 1. Now I'm going to do the derivative of that. So that means I got to use my power rule, so that's going to be negative. Leave the x alone, I'll put negative 1 there, and then you got to subtract 1 from the exponent. And now I'm going to simplify that, so that's negative 1 over x squared. Now our final answer to our original problem, though, is going to be 2 times whatever that is. And so our final answer is going to be negative 2 over x squared. So what I'm telling you by this constant multiplier rule is this 2 in the top, this guy, you can kind of disregard that 2 and just multiply it at the end. So this is the slide I got confused a second ago. This is the constant multiplier rule and the power rules being combined. So this slide here actually might be very helpful for you. So let's say you were trying to do the derivative of, let's just say 5x squared. Well, the constant multiplier rule tells you the following. It's c, well, c in this case would be 5. N is the exponent, so that's going to be 2. And then x, and then to the n minus 1, well, n was 2, so that's going to be 1. So in other words, this derivative is 10x. Sum and difference rules. The sum and difference rules are basically, what if you're taking multiple functions and adding them together, or multiple functions and subtracting them? Well, the easy way to think about it is this. The derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. In other words, just do the derivative of the first part minus the derivative of the second part. So here are some examples. So when you look at this x cubed minus 4x plus 5, you might start trying to think about how you're going to use the power rule. You're just going to use the power rule in each individual case. So that x to the third, when you do the derivative of that, that's going to become that 3x squared. That 4x, what's that going to become when we do the derivative? Well, that's just going to become 4. And then what's the derivative of a constant? Well, that's going to be just 0. And then just put the additions and subtractions between them. In other words, you're going to be left with f prime is equal to 3x squared minus 4. And then b is just another example if you'd like to try another one on your own. The derivatives of sine and cosine. Now these are more basic derivatives that you need to memorize. The first one is that the derivative of sine is cosine, which is very interesting. If we have time in class, I'll try to show you why that is. We can do an activity on that. The derivative of cosine is not sine. It's actually negative sine. So make a little note about that one. The derivative of sine is cosine, but the derivative of cosine is negative sine. So for example, let's say I want to look at the function f of x equals 2 sine x. Find f prime. Okay, I can do that. So first of all, I'm going to note that f prime is simply going to be 2 times the derivative of sine x. Notice I'm using my constant multiplier rule. My constant multiplier rule says that I'm taking a function times a constant. I can just pull that constant to the front. What is the derivative of sine x? Oh, we just talked about that. It's cosine x. And you are done. That is f prime of x, the derivative of 2 sine x. Okay, rates of change. You've seen how derivatives, how the derivative is used to determine slope. The derivative can also be used to determine rates of change. Applications of rates of change occur in a lot of different areas. So for examples, growth rates, production rates, water flow rates, velocities and accelerations, which we'll talk quite a bit about in this class. The function s that gives the position relative to the origin of a function is called the position function. So this is important stuff. You're gonna see questions in the future about the position function. If you've taken physics, you already kind of are familiar with this. If over a period of time delta t, the object changes its position by some amount delta s, remember s is the position, so delta s would be the change in position, then we know the formula that rate is distance divided by time. The average velocity, therefore, or the average rate of change, is simply going to be delta s over delta t. So consider a billiard ball that is dropped from a height of 100 feet. And its height s, s stands for position, at time t is given by the following position function. Where s is measured in feet and t is measured in seconds. Find the average velocity for each of the following. So guys, on all of these, all you're going to do is you're going to take delta S over delta T. So the change in the Y over the change in the X, or the change in position over the change in time. So I'm going to kind of let the power, I've already got these typed out to speed this up. So if I want to find the average rate of change over the interval from 1 to 2, well, the first thing I got to do is I got to figure out what the position is at time t equals 1. Well, it turns out that it's 84. At position 2, again, we're just plugging this. This is the position function. It's 36. So to find the average velocity, or delta S over delta T, it's going to be 36 minus 84 over 2 minus 1. This should look familiar. This is your basic slope formula from Algebra 1. In fact, this is kind of the only time in algebra, if you're taking a test or even the AP exam, that the question is really more of an Algebra 1 question than a calculus question. So it turns out that the average rate of change, or the average velocity of this billiard ball from time t equals 1 to t equals 2 is negative 48 feet per second. And it's negative because it's going in the downward direction. So here's another example of the same thing, except now instead of going from 1 to 2, it's going to 1.1 to 1.5. Here we see that the average rate of change there is now negative 40, not negative 48, which kind of makes sense. And then last but not least, we're only going to go from 1 to 1.1. So here, the change in the position is negative 3.36. The change in time is only 1/10 of a second. So the average rate of change here is negative 33.6 feet. Now, those three questions are average rates of change. Those aren't really calculus-y questions. They are, but you could have done that in algebra. You could have done all three of those in Algebra 1. Note that the average velocities are negative, indicating that the object is going down. Okay, so now here's what we really want to get to. In general, if S equals S of t is the position function of an object moving along a straight line, the velocity is given by the following. The limit as delta t goes to 0. So the previous three problems there in problem number 5, those were all average rates of change, average velocities. Now we want to know, how do we get the actual speed at an instant, or an instantaneous rate of change, or the actual velocity at any given time t? This is the answer. And by the way, it comes down to this. It's the derivative of the position function. And this should look familiar because this is our formal definition pretty much of a derivative. Velocity can be negative, 0, or positive. Speed of an object is just the absolute value of velocity. So speed cannot be negative. So this is our position function in general. Position function is 1/2 g, which is a gravitational constant, times t squared, plus the initial velocity, that's what v naught is, and s naught, s sub 0 there, or s naught, that's the initial position. Now we know that here on Earth, gravity is negative 32 feet per second, and then, or you could say that is negative 9.8 meters per second. So last example and we'll be done. Says using the derivative to find the velocity. So now we're going to find the instantaneous rate of change called velocity. At time t equals 0, a diver jumps from a platform and is 32 feet above the water. The position of the diver is given, and they give you the position function, where it's measured in feet and t is measured in seconds. When does the diver hit the water, and what's his velocity when he impacts? Well, to find t, where the diver hits, we're going to let s equal 0. Now that kind of, I hope that makes sense, because when s is equal to 0, we're saying the position is 0. In other words, he's hitting the water. So his position is now 0 feet above the ground. So this is our position function. So we set that equal to 0. We factor, and then we solve. And it says t is equal to -1 or 2 seconds. So do both those answers really make sense here? Well, probably the -1 does not. We're probably not thinking about at -1. So it's probably going to be just the positive. Since t is greater than 0, the positive value is what we're going to look at. So it's going to be 2 seconds. So it's going to take 2 seconds for him to hit the water. Okay, the velocity at time t is given by the derivative. So remember, our position function is here. This was s of t was given in the first slide as negative 16t squared plus 16t plus 32. If we do the derivative of that, or s prime of t, we're going to get negative 32t plus 16. So the velocity at time t equals 2. Now we just take that 2 and we plug it in for this t right here. And when we work that, we're going to get negative 48 feet per second. So at the time the diver hits, I'm sorry, at 2 seconds, which is when the instant that the diver hits the water, he is traveling at negative 48 feet per second. And that is that. So